Hi, welcome to the screencast for 12.2. 12.2 discusses intermolecular forces of attraction, and it's related to the kinetic molecular theory. But in this case, we're concentrating more on liquids and solids because remember, gases are so far apart that their intermolecular forces of attraction don't have any effect. It's like having a magnet too far away from anything metallic to have any effect on it. So intermolecular forces of attraction are a little bit difficult to understand because so far we've talked about what we call intramolecular forces. Intramolecular forces are what holds an individual particle together. So with an ionic compound, you have a positive ion and a negative ion, and those opposite charges hold that ionic crystal together. That's an intermolecular force. We call it an ionic bond. Metallic bonds. You've got metals, they have the sea of electrons. That holds an individual metal like aluminum or copper together. That's also an intermolecular force. And covalent bonds, the third intermolecular force that we've talked about. You've got a molecule sharing electrons so that both nonmetals can get stable. That is a covalent bond. So we've talked so far in chemistry about three different types of chemical bonds that hold individual particles together: ionic, metallic, and covalent. Now in chapter 12 we're going to talk just about covalent compounds, because remember, only covalent compounds are referred to as molecules. And covalent compounds have intermolecular forces. So these are the forces between like molecules. So water is a covalent compound. There are forces that hold a water molecule together. It's a very polar bond. But then there's also forces between water molecules that allow a water molecule or water molecules to form really nice raindrops. And water is a great example because we see drops of water around us all the time, and we know that water makes these really nice big round drops if we have the right conditions. So what's going on there? Okay, so just to review the strength of forces, there's three different kinds of forces that hold particles together: ionic bonds, metallic bonds, covalent bonds. Those are called intramolecular forces or chemical bonds. But now we're going to look at forces that hold surrounding particles together. What makes some things a solid at room temperature? What makes other things a gas at room temperature? This, for covalent compounds anyway, is all about the intramolecular forces. So these are called hydrogen bonds, dipole-dipole forces, and dispersion forces. So there's three different types that exist among covalently bonded molecules. If the molecules have weak forces between them, they'll most likely be a gas or maybe a liquid at room temperature. As that intermolecular force gets stronger, the particles are going to be pulled tighter together, have less freedom of movement, and they're more likely to be a solid at room temperature. So again, the three different types are dispersion forces, which are the really weak ones, dipole-dipole forces, which can be fairly weak to pretty strong. All depends on the amount of polarity or the difference in electronegativity. And then hydrogen bonds are the really strong ones. And this is what makes hair curly. I kid you not, it's really this thing called hydrogen bonds. And if you've had curly hair, you know how strong that bond is and how hard it is to break it and make it do something different. So let's start with dispersion forces. Dispersion forces are the weakest intermolecular force. It occurs in a covalent nonpolar substance, so where there's no charge, no dipoles, because the bonding electrons are shared equally. So this is going to be basically in a pure covalent substance like hydrogen gas or oxygen gas or nitrogen gas, and it's typically going to be a gas because it's a very weak force. So there's not going to be enough attractive force to keep those molecules close enough to form a liquid or a solid. So it explains why nonpolar liquids are hard to pour. If you've ever filled gasoline into your lawnmower or some other kind of engine, it dribbles every time. It doesn't matter how carefully you try not to dribble down the side of the lawnmower or your gas tank on your car. It dribbles. How come? Because gasoline has very little attraction for other gasoline molecules. So they just each do their own thing. It also explains why nonpolar liquids evaporate quickly. If you put rubbing alcohol on your skin, it's gone like 30 seconds. You put water on your skin, You wait for it to evaporate, you're going to be waiting a while unless you stand in front of a fan. And it also explains why nonpolar liquids don't freeze even in a Minnesota winter. Why do you think they call it antifreeze? The stuff you put in your radiator in the winter to keep it from freezing, that's nonpolar. Okay? So, dispersion forces, really weak, tend to be gases at room temperature. The middle one, dipole-dipole forces. Remember, a dipole just means two ends, two different charged ends. There's a positive end, there's a negative end. So by dipole-dipole forces, we mean the positive end of one molecule is going to tend to be attracted to the negative end of the other molecule. Makes sense, positive and negatives attract. Now the positive and negative within the molecule have the strongest attraction, so that molecule stays together. But you know, it's just like when you're dating someone, you can still window shop, and that's what these molecules do. There's still attraction for surrounding molecules. Not as strong as the attraction within the molecule, but there's some attraction. So molecules are going to tend to line up in what we call a head to tail fashion, or positive end of one near a negative end of another. It's stronger than dispersion forces, but it's going to be weaker than these unique hydrogen bonds. What makes a dipole-dipole force stronger or weaker? It's all about how polar the bond is. Remember, when you subtract electronegativity, you can have a difference as small as 0.1 or 0.2, so it's just barely polar. Those dipole forces aren't going to be very strong. Those might still be gases at room temperature, or maybe a liquid that doesn't pour very well. The dipole-dipole forces that get more and more electronegative get closer and closer to that 1.5, 1.6, you know, they're almost ionic bonds. Those are going to be a much stronger dipole-dipole force. Those are going to be a liquid or maybe even a solid at room temperature. So then what's a hydrogen bond? A hydrogen bond is just a really strong dipole-dipole bond. It's a unique dipole-dipole bond, like a dipole-dipole bond on steroids, okay? It occurs for the same reason. It's a positive end on one molecule attracting the negative end on the other one. But in the hydrogen bond, what makes it so crazy strong, stronger than any other dipole-dipole bond, is it's when hydrogen bonds with either fluorine or oxygen or nitrogen, and I think of it as the three fun atoms, F-O-N, and it's because those three atoms are very electronegative, yet they're very small because they're all in that same family, just up there in family 2, and they're bonding with hydrogen, which is also really small. And remember, when you put two really small things together, it's really hard to get them apart. So it's like two really powerful magnets. So hydrogen with fluorine, oxygen, or nitrogen is going to create this super strong, super unique dipole-dipole bond. And in fact, it's so strong, it gets this special name of a hydrogen bond. So it helps explain why water, H2O, which is about 18 grams per mole, is a solid or is a liquid at room temperature. It has a huge surface tension, which we'll talk about later. It's had a really high boiling point. Well, methane, CH4, which only weighs 16.05 grams per mole, so almost the same as water, has a really low surface tension, has a low boiling point, and it's a gas at room temperature. In fact, you know methane better as natural gas. So both molecules about the same size, same mass, and yet one's a liquid and closer to being a solid than it is a gas, because it does, you don't have to remove a lot of energy from room temperature for it to become a solid. Room temperature is about 22 degrees, 0 degrees it becomes a solid, but you'd have to heat it all the way to 100 degrees to get it to become a gas. And methane, on the other hand, is a gas, and you'd have to put a lot of pressure on it or get it really, really cold to get it into the liquid state. It's all about the intermolecular forces between. A couple other things about hydrogen bonds. It explains some of water's unique properties, and water is a very unique substance. It has a huge surface tension. By surface tension, we mean that when you belly flop into water, it hurts like the dickens, because water has like this protective skin on itself. It holds itself together really tightly. That's why we see nice round drops from water. It's why you could skip a rock across water, and it's why you can practically break your neck belly flopping into water. It has a really high boiling point for a covalent compound. It's a liquid at room temperature, while most covalent compounds this small are gases. And it even explains why water expands as it freezes to form ice. Water actually gets slightly bigger as it forms ice, which is why water is actually more dense as a liquid and less dense as a solid, which is really unusual. Most solids are more dense than their liquid state. So most solids will sink in liquids, but not ice, it floats. And it's because the hydrogen bond actually has to push the water molecules further apart so they have more space when they're in that set solid formation. As liquid molecules, they can be a little closer because they don't stay by each other that long. They're constantly moving and flowing. But when you're going to put water into a solid form, now all of a sudden that hydrogen bond pushes back, needs a little more space. To finish up then, well, what I consider some fun facts, you might consider them just, ho-hum. But again, this is what makes your hair curly, is the hydrogen bonds that are formed. Curly hair is kind of like the DNA spiral that you maybe remember seeing in biology. That's also a hydrogen bond. So if you want to straighten your hair, you have to break those hydrogen bonds. If you have straight hair and you want to curl it, you have to form those hydrogen bonds. That's what a perm is doing. It's trying to permanently alter those bonds. Another fun fact is geckos. You may be aware that geckos can climb on virtually anything. And it's not because they have sticky feet that a lot of people think about. It's because they have lots of little hairs on their feet that have very strong intermolecular forces. So they can set up an attraction between their feet and virtually any surface. Now, the one thing geckos can't climb is Teflon. And most of you know of Teflon. You maybe know of it as the anti-stick coating on your frying pan or whatever. But it was developed by NASA to decrease the friction on space vehicles as they re-entered Earth's atmosphere. When they came back into, a lot of air in one space, that creates an incredible amount of friction and heat. So Teflon was developed to help eliminate this. And Teflon coated surfaces now we use for all kinds of things. And geckos can't climb on Teflon coated surfaces.